how is angular momentum transferred from one bumper car to another? The answer to that question is that the first bumper car does an angular impulse on the second bumper car. Just as you can transfer energy by doing work and linear momentum by doing an impulse, you can transfer angular momentum by doing an angular impulse. So what exactly is an angular impulse? An angular impulse is a torque exerted for a time. For example, I can do an angular impulse on this bumper car by twisting it, that's the torque, as time passes. So here you go. Okay, I did an angular impulse on that bumper car and I transferred angular momentum to it. So that product, my torque times the time over which it acted, is the angular impulse and therefore the amount of angular momentum that I transfer to the bumper car. An angular impulse transfers a vector quantity, angular momentum, so that angular impulse itself is a vector quantity. It points in the direction of the torque that's responsible for it. So for example, if I twist the bumper car downward, I transfer downward angular momentum to the bumper car, so I did a downward angular impulse. On the other hand, if I twist it upward, that's upward torque produced an upward angular impulse that resulted in an upward transfer of angular momentum to the bumper car. And also, like impulses, I have some flexibility in the angular impulse I'm doing. For example, I can do the same angular impulse with different combinations of torque and time, or rather duration. For example, here is an angular impulse that involves a medium torque exerted for a medium amount of time. Here it goes. Okay. I transferred a certain amount of angular momentum, in this case downward, into the bumper car. And I did it with a medium torque exerted for a medium time. I could also use a much larger torque exerted for a very short time. And that was the same angular impulse, but with a bigger torque for a short time. And finally, I can do the same angular impulse with a smaller torque exerted for a longer time. It's a little hard, okay? But you get the idea. And in bumper cars, many of the twisting jolts that you experience, that you feel during the motion around the arena, occur during these collisions that transfer a lot of angular momentum in a very short period of time. And so they are high torque, short duration angular impulses that really spin you around hard. Also, like ordinary impulses, like the impulses that transfer momentum, angular impulses come in equal but opposite pairs. When I twist this bumper car downward, that's a downward twist I did on it, a downward transfer of angular momentum by way of a downward angular impulse, it does an angular impulse back on me in the opposite direction. So I transferred downward angular momentum to it. It, on the other hand, twisted me backwards because it has to. That's Newton's third law of rotational motion. It twisted me upward and did an angular impulse upward on me and gave me upward angular momentum, which is the same as a deficit, a negative amount of downward angular momentum. It took away the downward angular momentum that I gave to it, and that makes the transfer complete. I gave the bumper car downward angular momentum. At the same time, it took away downward angular momentum from me, so that what I lost, it gained. Angular momentum is conserved, and this has to happen. Whatever I give it, I have to give up. All right. Well, so far I'm just doing all of this with my hands in a bumper car. But in the bumper car arena, most of the angular impulses, and certainly the ones that are most exciting, involve collisions. And the angular impulses in those contexts, in the collision context, are kind of subtle. And they often involve frictional forces. So let me show you how an angular impulse occurs in bumper cars. As I say, they often involve friction, and so having these rubber bumpers, which have a lot of friction, they really grip each other pretty well, is important. Now, angular momentum like all the rotational quantities, is defined around about a center of rotation. So we have to pick it and stick with it. The center of rotation I'm going to pick is the center of mass of this car. This is our center of attention too. We're going to pay attention to this car. This guy is just an interloper. It's going to come through and spin the first car. At the start of the story, the angular momentum will be present already. It will be in the form of this car's moving around, in effect orbiting. It's going around the center of rotation for our story. It won't actually be traveling in a circle. It'll be traveling in a straight line as objects do when they're free of external forces. But the fact that it's moving like this means that it is swinging around that center of rotation. It's actually, there's rotation here already, and therefore angular momentum here already. So this guy's going to come along, and it's going to clip the edge of that bumper car. It's going to catch it and twist it. And the act of catching that edge and twisting that bumper car there, a force, a frictional force, exerted at a lever arm from the center of rotation produces a torque and will twist our main focus bumper car and do the angular impulse. So as this guy comes along heading straight and true, and it grabs the edge of the bumper car we care about, it's going to exert the torque for the time and do the angular impulse on that bumper car. So let me see if I can pull this off. What you should be looking for is this thing traveling straight, that one not spinning, the collision, and after that this guy should be because the angular momentum will be transferred from this one to our main focus. Ready, get set. There it is. Of course, I've got so much junk in the way. Let me get this out of the way. Come back, guys. It's spinning. Spinning. So, those kinds of collisions in bumper cars, I'm going to hold this guy and really clip it hard. It was spinning fast before it flew off onto the floor. But those kinds of collisions occur in real bumper cars, and all of a sudden you get clipped, your bumper car gets caught on the edge by a fast-moving nearby bumper car, and suddenly, whoa, you're spinning around. That's where that comes from. It's time for a question. This is a gyroscope, which consists of a wheel on an axle that's mounted in a frame that allows that wheel and axle to turn very freely, almost without any frictional torques at all. This particular gyroscope resides in a frame that isolates it from the external world so that it's very hard to exert any torques on this wheel, this gyroscope wheel, about the gyroscope wheel's center of mass, which is the center of rotation of this gyroscope. Now, there's a string wrapped around the axle of this gyroscope, and the question is this. If I pull that string while holding the frame so that axle can't move except to rotate, all it can do is rotate. If I pull the string while the axle is held in orientation, what will happen to the gyroscope? When I pull that string, I will produce a torque on the gyroscope about its center of mass, center of rotation. And that torque will last for a while, good fraction of a second. As a result, I will do a large angular impulse on the gyroscope and transfer a lot of angular momentum to it. And once I do, it'll be spinning fast. I'll show you. Here we go. It's now spinning quite fast, and it has a lot of angular momentum. And the interesting thing to show is that as I try to move the surroundings, the frame that holds this gyroscope in place, it tends to keep turning about the same axis. As long as I don't exert a torque on it, I transfer no angular momentum to it about its own center of rotation, and it keeps turning as it was. Now, it's not perfect. It's pretty close. But the frame really tries to prevent any angular impulses on that spinning gyroscope. All right. Now, in my bumper car arena, which I'll bring out in a moment, I have bumper cars that don't have rubber bumpers. They're all plastic. They don't have very much friction between them. And so when one clips the other one, it doesn't transfer very much angular momentum to the one it hit. I can help that by making my bumper cars not perfectly round, not circular like this. And many bumper cars aren't quite circular. And when they're not circular, it isn't just frictional forces that contribute to those torques. It's also support forces. So I'm going to bring out my little bumper car arena, and I'm going to put on some bumper cars that I've made not round. So here we have my miniature bumper car arena again, and I've modified two of the bumper cars by putting wires on them that stick out. And those wires will allow a passing bumper car to exert a large torque on these modified bumper cars. So that makes them more similar to bumper cars that have either rubber bumpers that give you a lot of grip, or to bumper cars that aren't circular, that extend outward in certain areas so that a passing bumper car can exert support forces on that bumper car and produce torque in that manner. So first, to show you that a passing bumper car, let me pick a different color, the green one passing the red one will catch its wire, exert the torque on the red bumper car about the red bumper car's center of mass, which will be our center for the story, and it will set the red bumper car spinning by doing an angular impulse on the red bumper car. So I'll start with the red bumper car as motionless as I can get it. Here it is, motionless, bumper car spinning. There it goes. And I can do the same with the little red bumper car. I only have little red bumper cars, and I can set it spinning. Where things get a little more interesting, though, are when I have bumper cars of different masses bumping into each other. For example, this bumper car, this big red one, has a relatively large rotational mass. And so you have to pour a lot of angular momentum into that in order to make its angular velocity significant. So let me smack a small, one of the little red guys, into that big red behemoth. Not much action. The little red one carried the angular momentum at the start. It has a small mass and therefore had a relatively small rotational mass about the center of the big red one. So it didn't have much angular momentum to transfer. It transferred a good fraction of what it had, but that wasn't enough to set the big red one with its large rotational mass spinning very fast. On the other hand, if we go use the little red one as a target and take well, now I can use a big green one as the passing monster, it sets the little red one spinning furiously because the big green one was carrying a lot of rotation, a lot of angular momentum. It has a big mass, and as it moved around the center of rotation, which was the center of mass of our little one, the green one was carrying a lot of angular momentum. The little red one received a good fraction of that angular momentum from the green one, and that was enough to make the little red one with its tiny rotational mass spin like crazy. So you've seen these effects in bumper cars if you've gone there or experienced them, and that is that big massive cars passing you and clipping the edge of your car can really cause some serious angular response from your car. Your car receives a big dose of angular momentum by way of a big angular impulse, and suddenly, woof, you're whipped around in a hurry. On the other hand, passing cars that are occupied by, say, small children don't carry very much angular momentum about your center of mass. And so when they give you even a good fraction of their angular momentum, doesn't have much effect on you and your car. Your car receives a modest angular momentum dose by way of a modest angular impulse, and the result is underwhelming. So once again, the big, massive cars affect the little cars a lot more than the other way around. Well, that's it for the story of angular impulses on the bumper car arena. The next and final topic on which I want to talk about is what happens if the bumper car arena isn't perfectly flat. How do the bumper cars move when they're on a surface that is uneven? And that's the topic for the next video.